Livewired, the inside story of the ever-changing brain, by David Eagleman, abridged, read by Vincent Bagnall. Every man is born as many men and dies as a single one. Martin Heidegger. Chapter 1. The Electric Living Fabric. Imagine this. Instead of sending a 400-pound rover vehicle to Mars, we merely shoot over to the planet a single sphere, one that can fit on the end of a pin. Using energy from sources around it, the sphere divides itself into a diversified army of similar spheres. The spheres hang on to each other and sprout features: wheels, lenses, temperature, sensors, and a full internal guidance system. You'd be gobsmacked to watch such a system discharge itself, but you only need to go to any nursery to see this unpacking in action. You'll see wailing babies who began as a single microscopic fertilized egg and are now in the process of emancipating themselves into enormous humans, replete with photon detectors, multi-jointed appendages, pressure sensors, blood pumps, and machinery for metabolizing power from all around them. But this isn't even the best part about humans. There's something more astonishing. Our machinery isn't fully pre-programmed, but instead shapes itself by interacting with the world. As we grow, we constantly rewrite our brain's circuitry to tackle challenges, leverage opportunities, and understand the social structures around us. Our species has successfully taken over every corner of the globe because we represent the highest expression of a trick that Mother Nature discovered. Don't entirely prescript the brain. Instead, just set it up with the basic building blocks and get it into the world. The bawling baby eventually stops crying, looks around, and absorbs the world around it. It molds itself to the surroundings. It soaks up everything from local language to broader culture to global politics. It carries forward the beliefs and biases of those who raise it. Every fond memory it possesses, every lesson it learns, every drop of information it drinks, all these fashion its circuits to develop something that was never pre-planned, but instead reflects the world around it. This book will show how our brains incessantly reconfigure their own wiring, and what that means for our lives and our futures. Along the way, we'll find our story illuminated by many questions. Why did people in the 1980s, and only in the 1980s, see book pages as slightly red? Why is the world's best archer armless? Why do we dream each night? And what does that have to do with the rotation of the planet? What does drug withdrawal have in common with a broken heart? Why is the enemy of memory not time, but other memories? How can a blind person learn to see with her tongue, or a deaf person learn to hear with his skin? Might we someday be able to read the rough details of someone's life from the microscopic structure etched in their forest of brain cells? The Child with Half a Brain. While Valerie S. was getting ready for work, her 3-year-old son Matthew collapsed on the floor. He was unarousable. His lips turned blue. Valerie called her husband in a panic. "Why are you calling me?" he bellowed. "Call the doctor." A trip to the emergency room was followed by a long aftermath of appointments. The pediatrician recommended Matthew have his heart checked. The cardiologist outfitted him with a heart monitor, which Matthew kept unplugging. All the visits surfaced nothing in particular. The scare was a one-off event. Or so they thought. A month later, while he was eating, Matthew's face took on a strange expression. His eyes became intense. His right arm stiffened and straightened up above his head. He remained unresponsive for about a minute. Again, Valerie rushed him to the doctors. Again, there was no clear diagnosis. Then it happened again the next day. A neurologist hooked up Matthew with a cap of electrodes to measure his brain activity, and that's when he found the telltale signs of epilepsy. Matthew was put on seizure medications. The medications helped, but not for long. Soon Matthew was having a series of intractable seizures, separated from one another first by an hour, then by 45 minutes, then by 30 minutes, like the shortening durations between a woman's contractions during labor. After a time, he was suffering a seizure every 2 minutes. Valerie and her husband, Jim, hurried Matthew to the hospital each time such a series began, and he'd be housed there for days to weeks. After several stints of this routine, they would wait until his contractions had reached the 20-minute mark, and then call ahead to the hospital, climb in the car, and get Matthew something to eat at McDonald's on the way there. Matthew, meanwhile, labored to enjoy life between seizures. The family checked into the hospital 10 times each year. This routine continued for 3 years. Valerie and Jim began to mourn the loss of their healthy child, not because he was going to die, but because he was no longer going to live a normal life. They went through anger and denial. Their normal changed. Finally, during a 3-week hospital stay, the neurologists had to allow that this problem was bigger than they knew how to handle at the local hospital. So, the family took an air ambulance flight from their home in Albuquerque, New Mexico, to Johns Hopkins Hospital in Baltimore. It was here, in the pediatric intensive care unit, that they came to understand that Matthew had Rasmussen's encephalitis, a rare chronic inflammatory disease. The problem with the disease is that it affects not just a small bit of the brain, but an entire half. Valerie and Jim explored their options and were alarmed to learn there was only one known treatment for Matthew's condition, a hemispherectomy, or the surgical removal of an entire half of the brain. "I can't tell you anything the doctors said after that," Valerie told me. "One just shuts down, like everyone's talking a foreign language." Valerie and Jim tried other approaches, but they proved fruitless. When Valerie called Johns Hopkins Hospital to schedule the hemispherectomy some months later, the doctors asked her, "Are you sure?" "Yes," she said. "Can you look in the mirror every day and know you've chosen what you've needed to do?" Valerie and Jim couldn't sleep beneath the crushing anxiety. Could Matthew survive the surgery? Was it even possible to live with half of the brain missing? And even if so, would the removal of one hemisphere be so debilitating as to offer Matthew a life on terms not worth taking? But there were no more options. A normal life couldn't be lived in the shadow of multiple seizures each day. They found themselves weighing Matthew's assured disadvantages against an uncertain surgical outcome. Matthew's parents flew him to the hospital in Baltimore. Under a small, child-sized mask, Matthew drifted away into the anesthesia. A blade carefully opened a slit in his shaved scalp. A bone drill cut a circular burr hole in his skull. Working patiently over the course of several hours, the surgeon removed half of the delicate pink material that underpinned Matthew's intellect, emotion, language, sense of humor, fears, and loves. The extracted brain tissue, useless outside its biological milieu, was banked in small containers. The empty half of Matthew's skull slowly filled up with cerebrospinal fluid, appearing in neuroimaging as a black void. In the recovery room, his parents drank hospital coffee and waited for Matthew to open his eyes. What would their son be like now? Who would he be with only half a brain? Of all the objects our species has discovered on the planet, nothing rivals the complexity of our own brains. The human brain consists of 86 billion cells called neurons, cells that shuttle information rapidly in the form of traveling voltage spikes. Neurons are densely connected to one another in intricate forest-like networks, and the total number of connections between the neurons in your head is in the hundreds of trillions, around 0.2 quadrillion. To calibrate yourself, think of it this way. There are 20 times more connections in a cubic millimeter of cortical tissue than there are human beings on the entire planet. But it's not the number of parts that make a brain interesting. It's the way those parts interact. In textbooks, media advertisements, and popular culture, the brain is typically portrayed as an organ with different regions dedicated to specific tasks. This area here exists for vision. That swath there is necessary for knowing how to use tools. This region becomes active when resisting candy, and that spot lights up when mulling over a moral conundrum. All the areas can be neatly labeled and categorized. But that textbook model is inadequate, and it misses the most interesting part of the story. The brain is a dynamic system, constantly altering its own circuitry to match the demands of the environment and the capabilities of the body. If you had a magical video camera with which to zoom in to the living, microscopic cosmos inside the skull, you would witness the neurons' tentacle-like extensions grasping around, feeling, bumping against one another, searching for the right connections to form or forego, like citizens of a country establishing friendships, marriages, neighborhoods, political parties, vendettas, and social networks. Think of the brain as a living community of trillions of intertwining organisms. Much stranger than the textbook picture, the brain is a cryptic kind of computational material, a living three-dimensional textile that shifts, reacts, and adjusts itself to maximize its efficiency. The elaborate pattern of connections in the brain, the circuitry, is full of life. Connections between neurons ceaselessly blossom, die, and reconfigure. You are a different person than you were at this time last year because your brain has woven itself into something new. When you learn something, the location of a restaurant you like, a piece of gossip about your boss, that addictive new song on the radio, your brain physically changes. The same thing happens when you experience a financial success, a social fiasco, or an emotional awakening. When you shoot a basketball, disagree with a colleague, fly into a new city, gaze at a nostalgic photo, or hear the mellifluous tones of a beloved voice. The immense intertwining jungles of your brain work themselves into something slightly different from what they were a moment before. These changes sum up to our memories, the outcome of our living and loving. Accumulating over minutes and months and decades, the innumerable brain changes tally up to what we call you. Or at least, the you right now. Yesterday, you were marginally different, and tomorrow, you'll be someone else again. Life's other secret. In 1953, Francis Crick burst into the Eagle and Child pub. He had announced to the startled Swillers that he and James Watson had just discovered the secret of life. They had deciphered the double helical structure of DNA. It was one of the great pub-crashing moments of science. But it turns out that Crick and Watson had discovered only half the secret. The other half, you won't find written in a sequence of DNA-based pairs, and you won't find it written in a textbook. Not now, not ever. Because the other half is all around you. It is every bit of experience you have with the world. The textures and tastes, the caresses and car accidents, the languages and love stories. To appreciate this, imagine you were born 30,000 years ago. You have exactly your same DNA. But you slide out of the womb and open your eyes onto a different time period. What would you be like? Would you relish dancing in pelts around the fire while marveling at stars? Would you bellow from a treetop to warn of approaching saber-toothed tigers? Would you be anxious about sleeping outdoors when rain clouds bloomed overhead? Whatever you think you'd be like, you're wrong. It's a trick question, because you wouldn't be you. Not even vaguely. This caveman with identical DNA might look a bit like you as a result of having the same genomic recipe book. But the caveman wouldn't think like you, nor would the caveman strategize, imagine, love, or simulate the past and future quite as you do. Why? Because the caveman's experiences are different from yours. Although DNA is a part of the story of your life, it is only a small part. The rest of the story involves the rich details of your experiences and your environment, all of which sculpt the vast microscopic tapestry of your brain cells and their connections. What we think of as you is a vessel of experience into which is poured a small sample of space and time. You imbibe your local culture and technology through your senses. Who you are owes as much to your surroundings as it does to the DNA inside you. Contrast this story with a Komodo dragon born today and a Komodo dragon born 30,000 years ago. Presumably, it would be more difficult to tell them apart by any measure of their behavior. What's the difference? Komodo dragons come to the table with a brain that unpacks to approximately the same outcome each time. The skills on their resume are mostly hardwired: eat, mate, swim. And these allow them to fill a stable niche in the ecosystem. But they're inflexible workers. If they were airlifted from their home in southeastern Indonesia and relocated to snowy Canada, there would soon be no more Komodo dragons. In contrast, humans thrive in ecologies around the globe. And soon enough, we'll be off the globe. What's the trick? It's not that we're tougher, more robust, or more rugged than other creatures. Along any of these measures, we lose to almost every other animal. Instead, it's that we drop into the world with a brain that's largely incomplete. As a result, we have a uniquely long period of helplessness in our infancy. But that cost pays off because our brains invite the world to shape them. And this is how we thirstily absorb our local languages, cultures, fashions, politics, religions, and moralities. Dropping into the world with a half-baked brain has proven a winning strategy for humans. We have outcompeted every species on the planet, covering the land mass, conquering the seas, and bounding onto the moon. We have tripled our lifespans, we compose symphonies, erect skyscrapers, and measure with ever-increasing precision the details of our own brains. None of these enterprises were genetically encoded. At least they weren't encoded directly. Instead, our genetics bring about a simple principle. Don't build inflexible hardware. Build a system that adapts to the world around it. Our DNA is not a fixed schematic for building an organism. Rather, it sets up a dynamic system that continually rewrites its circuitry to reflect the world around it and to optimize its efficacy within it. Think about the way a schoolchild will look at the globe of the earth and assume there is something fundamental and unchanging about the country borders. In contrast, a professional historian understands that country borders are functions of happenstance and that our story could have been run with slight variations. A would-be king dies in infancy, or a corn pestilence is avoided, or a warship sinks and a battle tips the other way. Small changes would cascade to yield different maps of the world. And so it goes with the brain. Although a traditional textbook drawing suggests that neurons in the brain are happily packed next to one another like jelly beans in a jar, don't let the cartoon fool you. Neurons are locked in competition for survival. Just like neighboring nations, neurons stake out their territories and chronically defend them. They fight for territory and survival at every level of the system. Each neuron and each connection between neurons fights for resources. As the border wars rage through the lifetime of a brain, maps are redrawn in such a way that the experiences and goals of a person are always reflected in the brain's structure. If an accountant drops her career to become a pianist, the neural territory devoted to her fingers will expand. If she becomes a microscopist, her visual cortex will develop higher resolution for the small details she seeks. If she becomes a perfumer, her brain regions assigned to smell will enlarge. It is only from a dispassionate distance that the brain gives the illusion of a globe with predestined and definitive borders. The brain distributes its resources according to what's important, and it does so by implementing do-or-die competition among all the parts that make it up. This basic principle will illuminate several questions we'll encounter shortly. Why do you sometimes feel as though your cell phone just buzzed in your pocket, only to discover it's on the table? Why does the Austrian-born actor Arnold Schwarzenegger have a thick accent when he speaks American English, while the Ukrainian-born actress Mila Kunis has none? Why is a child with autistic savant syndrome able to solve a Rubik's Cube in 49 seconds, but unable to hold a normal conversation with a peer? Can humans leverage technology to build new senses, thus gaining a direct perception of infrared light, global weather patterns, or the stock market? If you're missing the tool, create it. Chapter 2. Just add world. How to grow a good brain. Brains are not born into the world of blank slates. Instead, they arrive pre-equipped with expectations. Consider the birth of a baby chicken, moments after hatching. It wobbles around on its little legs and can clumsily run and dodge. In its environment, it simply doesn't have time to spend months or years learning how to move around. Human infants as well come to the table with a good deal of pre-programming. Take the fact that we come pre-equipped to absorb language, or that babies will mimic an adult sticking out her tongue, a feat requiring a sophisticated ability to translate vision into motor action. Or that fibers from your eye don't need to learn how to find their targets deep in the brain. They simply follow molecular cues and hit their goal every time. For all this sort of hardwiring, we can thank our genes. But genetic hardwiring does not provide the whole story, especially for humans. The system's organization is too complex, and the genes are far too few. Even when you take into account the slicing and dicing that produces many different flavors of the same gene, the number of neurons and their connections vastly outstrips the number of genetic combinations. So we know that the details of brain wiring involve more than the genetics. And 2 centuries ago, thinkers began to correctly suspect that the details of experience carried importance. In 1815, the physiologist Johann Spurzheim proposed that the brain, like the muscles, could be increased by exercise. His idea was that blood carried with it the nutrition for growth, and that it was carried in greater abundance to the parts which are excited. By 1874, Charles Darwin wondered if this basic idea might explain why rabbits in the wild had larger brains than domestic rabbits. He suggested that the wild hares were forced to use their wits and senses more than the domesticated ones, and that the size of their brains followed. In the 1960s, researchers began to study in earnest whether the brain could change in measurable ways as a direct result of experience. The simplest way to examine the question was to raise rats in different environments. For example, a rich environment packed with toys and running wheels, or the deprived environment of an empty and solitary cage. The results were striking. The environment altered the rat's brain structure, and the structure correlated with the animal's capacity for learning and memory. The rats raised in enriched environments performed better at tasks, and were found at autopsy to have long, lush dendrites, the tree-like branches growing from the cell body. In contrast, rats from the deprived environments were poor learners and had abnormally shrunken neurons. This same effective environment is found in birds, monkeys, and other mammals. To the brain, context matters. A neuron normally grows like a branched tree, allowing it to connect to other neurons. In an enriched environment, branches grow more lavishly. In a deprived environment, branches shrivel. Does the same happen in humans? In the early 1990s, researchers in California realized they could take advantage of autopsies to compare the brains of those who completed high school with those who completed college. In analogy to the animal studies, they found that an area involved in language comprehension contained more elaborate dendrites in the college-educated. So the first lesson is that the fine structure of the brain reflects the environment to which it is exposed. And this is not just about the dendrites. As we'll learn shortly, world experience modulates almost every measurable detail of the brain, from the molecular scale to overall brain anatomy. Experience necessary. Why was Einstein Einstein? Well, surely genetics mattered, but he is affixed to our history books because of every experience he'd had. The exposure to cellos, the physics teacher he had in his senior year, the rejection of a girl he loved, the patent office in which he worked, the math problems he was praised for, the stories he read, and millions of further experiences, all of which shaped his nervous system into the biological machinery we distinguish as Albert Einstein. Each year there are thousands of other children with his potential but who are exposed to cultures, economic conditions, or family structures that don't give sufficiently positive feedback, and we don't call them Einsteins. If DNA were the only thing that mattered, there would be no particular reason to build meaningful social programs to pour good experiences into children and protect them from bad experiences. But brains require the right kind of environment if they are to correctly develop. When the first draft of the Human Genome Project came to completion at the turn of the millennium, one of the great surprises was that humans have only about 20,000 genes. And this number came as a surprise to biologists. Given the complexity of the brain and the body, it had been assumed that hundreds of thousands of genes would be required. So how does the massively complicated brain, with its 86 billion neurons, get built from such a small recipe book? The answer pivots on a clever strategy implemented by the genome. Build incompletely and let world experience refine. Thus, for humans at birth, the brain is remarkably unfinished, and interaction with the world is necessary to complete it. Consider the sleep-wake cycle. This internal clock, known as the circadian rhythm, runs roughly on a 24-hour cycle. However, if you descend into a cave for several days, where there are no clues to the light and dark cycles of the surface, your circadian rhythm would drift in a range between 21 and 27 hours. And this exposes the brain's simple solution. Build a non-exact clock and then calibrate it to the sun's cycle. With this elegant trick, there's no need to genetically code a perfectly wound clock. The world does the winding. The flexibility of the brain allows the events in your life to stitch themselves directly into the neural fabric. It's a great trick on the part of Mother Nature, allowing the brain to learn languages, ride bicycles, and grasp quantum physics, all from the seeds of a small collection of genes. Our DNA is not a blueprint. It is merely the first domino that kicks off the show. From this viewpoint, it is easy to understand why some of the most common problems of vision, such as the inability to see depth correctly, develop from imbalances in the pattern of activity delivered to the visual cortex by the two eyes. For example, when children are born cross-eyed or wall-eyed, the activity from the two eyes is not well correlated, as it would be with aligned eyes. If the problem is not addressed, the child will not develop normal stereo vision, that is, the capacity to determine depth from the small differences between what the two eyes are seeing. One eye will grow progressively weaker, often to the point of blindness. But the important point is that the development of normal visual circuits relies on normal visual input. It is experience dependent. So genetic instructions play only a minor role in the detailed assembly of cortical connections. It couldn't be any other way. With 20,000 genes and 200 trillion connections between neurons, how could the details possibly be pre-specified? That model could never have worked. Instead, neuronal networks require interaction with the world for their proper development. Chapter 3. The inside mirrors the outside. The case of the Silver Spring monkeys. In 1951, the neurosurgeon Wilder Penfield sank the tip of a fine electrode into the brain of a man undergoing surgery. Along the brain tissue just beneath where one might wear headphones, Penfield discovered something surprising. If he gave a small shock of electricity at a particular spot, the patient would feel as though his hand were being touched. If Penfield stimulated a nearby spot, the patient would feel the touch on his torso, a different spot, the knee. Every spot on the patient's body was represented in the brain. Then Penfield made a deeper realization. Neighboring parts of the body were represented by neighboring spots on the brain. The hand was represented near the forearm, which was represented near the elbow, which was represented near the upper arm, and so on. Along this strip of the brain, there was a detailed map of the body. By moving from spot to spot slowly along the somatosensory cortex, he could find the whole human figure. And this wasn't the only map he found. Along the motor cortex, the strip just in front of the somatosensory cortex, he discovered the same kind of result. A little zap of electricity caused muscles to twitch in specific neighboring areas of the body. Again, it was laid out in an orderly manner. He named these maps of the body the homunculus or little man. The maps of the body are found where inputs enter the brain, somatosensory cortex, and outputs leave the brain, motor cortex. Areas with more detailed sensation, and those that are more finely controlled, command more real estate. But the existence of the maps is strange and unexpected. How do they exist? After all, the brain is locked in total darkness within the skull. And these 3 pounds of tissue don't know what your body looks like. The brain has no way to directly see your body. It has access to nothing but a chattering stream of electrical pulses racing up the thick bundles of data cables we call nerves. Stowed away in its bony prison, the brain should have no idea what limbs are connected where, or which are next to which others. So how is there a depiction of the body's layout in this lightless vault? A moment of thought will likely lead you to the most straightforward solution. The map of the body must be genetically pre-programmed. Good guess, but wrong. Instead, the answer to the mystery is more fiendishly clever. A clue to the map mystery came decades later in an unexpected turn of events. Edward Taub, a scientist at the Institute of Behavioral Research in Silver Spring, Maryland, wanted to understand how victims of brain injury could recover movement. To that end, he obtained 17 monkeys and studied whether severed nerves could regenerate. In each, he carefully cut a nerve bundle that linked the brain to one of the arms or one of the legs. As expected, the unfortunate monkeys lost all sensation from the affected limbs, and Taub set about studying whether there was a way to get the monkeys to regain use. In 1981, a young volunteer named Alex Pacheco began to work in the lab. Although he presented himself as an intrigued student, in fact, he was there to spy for a budding organization, the People for the Ethical Treatment of Animals. At night, Pacheco took photographs. Some of the shots were apparently staged to exaggerate the suffering of the monkeys, but in any case, the effect was achieved. In September 1981, the Montgomery County Police raided the laboratory and shut it down. Dr. Taub was convicted of 6 counts of failure to provide adequate veterinary care. All of the charges were overturned on appeal. Nonetheless, the events led to the creation of the Animal Welfare Act of 1985, in which Congress defined new rules for animal care in research environments. Although this provided a watershed moment for animal rights, the importance of the story is not only about what happened in Congress. For our purposes here, it's about what happened to the 17 monkeys. Immediately after the accusation, People for the Ethical Treatment of Animals swept in and absconded with the monkeys, leading to charges of theft of court evidence. Incensed, Taub's research institution demanded the return of the monkeys. The legal battle grew increasingly heated. The battle for possession of the monkeys ascended to the U.S. Supreme Court. The court rejected PETA's plea to keep the monkeys, instead granting custody to a third party, the National Institutes of Health. And while humans barked at each other in distant courtrooms, the disabled monkeys enjoyed an early retirement by eating, drinking, and playing together for 10 years. Near the end of this period, one of the monkeys became terminally ill. The court agreed that the monkey could be put to sleep, and here's where the plot turned. A group of neuroscience researchers made a proposal to the judge. The monkey's severed nerve would not have been in vain if the researchers could be allowed to perform a brain mapping study on the monkey while it was under anesthesia, just before being euthanized. After some debate, the court granted permission. On January 14, 1990, the research team put recording electrodes in the monkey's somatosensory cortex, exactly as Wilder Penfield had done with his human patient. The researchers touched the monkey on its hand, arm, face, and so on, while recording from neurons in the brain. In this way, they revealed the map of the body in the brain. The findings sent ripples through the neuroscience community. The body map had changed over the years. Unsurprisingly, a gentle touch on the monkey's nerve-severed hand no longer activated any response in the cortex. But the surprise was that the little bit of cortex that used to represent the hand was now excited by a touch to the face. The map of the body had reorganized. The homunculus still looked like a monkey, but a monkey without a right arm. This discovery ruled out the possibility that the brain's map of the body is genetically pre-programmed. Instead, something much more interesting was going on. The brain's map was flexibly defined by active inputs from the body. When the body changes, the homunculus follows. The same brain mapping studies were done later in the year on the other Silver Spring monkeys. In each one of them, the somatosensory cortex had dramatically rearranged. The areas once representing the nerve-severed limbs had been taken over by neighboring areas in the cortex. The homunculi had transformed to match the monkey's new body plans. What does it feel like when the brain reorganizes like that? Unfortunately, monkeys can't tell us, but people can. The afterlife of Lord Horatio Nelson's right arm. The British naval commander, Admiral Lord Horatio Nelson, who lived from 1758 to 1805, is the hero mounted high on a pedestal overlooking London's Trafalgar Square. The statue stands in towering testimony to his charismatic leadership, his tactical strength, and his inventive stratagems, which together led to decisive victories on waters from the Americas to the Nile to Copenhagen. He died heroically in his final showdown, the Battle of Trafalgar, one of Britain's greatest maritime victories. Beyond his naval impact, Admiral Nelson also contributed to neuroscience. However, this was totally accidental. His involvement began during his attack on Santa Cruz de Tenerife, when at 11 o'clock at night on July 24, 1797, a musket ball exited a Spanish rifle barrel at 1,000 feet per second and ended its trajectory in Lord Nelson's right arm. His bone shattered. Nelson's stepson tied a piece of his neck scarf tightly around the arm to stop the bleeding, and Nelson's sailors rowed vigorously back to the main ship, where the surgeon tensely awaited. After a rapid physical exam, the good news was that Nelson was likely to survive. The bad news was Nelson's right arm was surgically removed above the elbow and thrown overboard into the water. Over the following weeks, Nelson learned to function without his right arm, eating, washing himself, even shooting. He came to jokingly refer to the stump of his amputation as his fin. But some months after the event, strange consequences began. Lord Nelson started to feel that his arm was still present. He experienced sensations from it. He was certain that his missing fingernails from his missing fingers were digging painfully into his missing right palm. Nelson had an optimistic interpretation of this sensation of his phantom limb. He concluded that he now possessed incontrovertible proof of life after death. After all, if an absent limb could give rise to conscious feeling, an ever-present ghost of itself, then an absent body must as well. Chapter 4. Wrapping around the inputs. Every man can, if he so desires, become the sculptor of his own brain. Santiago Ramon y Cajal, who lived from 1852 to 1934, neuroscientist and Nobel laureate. Michael Chorost was born with poor hearing, and he got by during his young adult life with the help of a hearing aid. But one afternoon, while waiting to pick up a rental car, the battery to his hearing aid died, or so he thought. He replaced the battery but found that all sound was still missing from his world. He drove himself to the nearest emergency room and discovered that the remainder of his hearing, his thin auditory lifeline to the rest of the world, was gone for good. Hearing aids wouldn't be of any use for him now. After all, they work by capturing sound from the world and blasting it at higher volume into the ailing auditory system. This strategy is effective for some types of hearing loss, but it only works if everything downstream of the eardrum is functioning. If the inner ear is defunct, no amount of amplification solves the problem. And this was Michael's situation. It seemed as though his perception of the world's soundscapes had come to an end. But then he found out about a single remaining possibility, and in 2001 he underwent surgery for a cochlear implant. This tiny device circumvents the broken hardware of the inner ear to speak directly to the functioning nerve, think of it like a data cable, just beyond it. The implant is a mini computer lodged directly into his inner ear. It receives sounds from the outside world and passes the information to the auditory nerve by means of tiny electrodes. So the damaged part of the inner ear is bypassed, but that doesn't mean the experience of hearing comes for free. Michael had to learn to interpret the foreign language of the electrical signals being fed to his auditory system. When the device was turned on a month after surgery, the first sentence I heard sounded like zzz, viz, or viz. My brain gradually learned how to interpret the alien signal. Before long, zzz, viz, or viz became, "What did you have for breakfast?" After months of practice, I could use the telephone again, even converse in loud bars and cafeterias. Although being implanted with a mini-computer sounds something like science fiction, cochlear implants have been on the market since 1982, and more than 500,000 people are walking around with these bionics in their heads, enjoying voices and door knocks and laughter and piccolos. The software on the cochlear implant is hackable and updatable, so Michael has spent years getting more efficient information through the implant without further surgeries. Almost a year after the implant was activated, he upgraded to a program that gave him twice the resolution. As Michael puts it, "While my friends' ears will inevitably decline with age, mine will only get better." Terry Byland lives near Los Angeles. He was diagnosed with retinitis pigmentosa, a degenerative disorder of his retina, the sheet of photoreceptors at the back of the eye. He reports, aged 37, "The last thing you want to hear is that you are going blind." that there's nothing they can do. But then he discovered that there was something he could do if he was brave enough to try it. In 2004, he became one of the first patients to undergo an experiment procedure, getting implanted with a bionic retinal chip, a tiny device with a grid of electrodes. It plugs into the retina at the back of the eye. A camera on glasses wirelessly beams its signals to the chip. The electrodes give little zaps of electricity to Terry's surviving retinal cells, generating signals along the previously silent highway of the optic nerve. After all, Terry's optic nerve functioned just fine, even while the photoreceptors had died. The nerve remained hungry for signals it could carry to the brain. A research team at the University of Southern California implanted the miniature chip in Terry's eye. The surgery was completed without a hitch, and then the real testing began. With hushed anticipation, the research team turned on the electrodes individually to test them. Terry reported, "It was amazing to see something. It was like little specks of light, not even the size of a dime, when they were testing the electrodes one by one." Over the course of days, Terry experienced only small constellations of lights, not a rousing success, but his visual cortex gradually figured out how to extract better information out of the signals. After such time, he detected the presence of his 18-year-old son. "I was with my son walking. It was the first time I had seen him since he was 5 years old." I don't mind saying there were a few tears wept that day. Terry wasn't experiencing a clear visual picture. It was more like a simple, pixelated grid, but the door of darkness had swung open a crack. Over time, his brain has been able to make better sense of the signals. While he can't ascertain the details of individual faces, he can make them out dimly. And although the resolution of his retinal chip is low, he can touch objects presented at random locations and is able to cross a city street by discerning the white lines of the crosswalk. He proudly reports, "When I'm in my home or another person's house, I can go into any room and switch the light on, or see the light coming in through the window. When I am walking along the street, I can avoid low-hanging branches. I can see the edges of the branches, so I can avoid them." The idea of prosthesis for the ear and eye had been seriously considered in the scientific community for decades, but no one was positive that these technologies would work. After all, the inner ear and the retina perform astoundingly sophisticated processing on the sensory input they receive. So would a small electronic chip, speaking the dialect of Silicon Valley instead of the language of our natural biological sense organs, be understood by the rest of the brain? Or instead, would its patterns of miniature electrical sparks come off as gibberish to downstream neural networks? These devices would be like an uncouth traveler to a foreign land who expects that everyone will figure out his language if he just keeps shouting it. Amazingly, in the case of the brain, such an unrefined strategy works. The rest of the country learns to understand the foreigner. But how? The key to understanding this requires diving one level deeper. Your 3 pounds of brain tissue are not directly hearing or seeing any of the world around you. Instead, your brain is locked in a crypt of silence and darkness inside your skull. All it ever sees are electrochemical signals that stream in along different data cables. That's all it has to work with. In ways we are still working to understand, the brain is stunningly gifted at taking in these signals and extracting patterns. To those patterns, it assigns meaning. With the meaning, you have subjective experience. The brain is an organ that converts sparks in the dark into the euphonious picture show of your world. All of the hues and aromas and emotions and sensations in your life are encoded in trillions of signals zipping in blackness. Just as a beautiful screensaver on your computer screen is fundamentally built of zeros and ones. Chapter 5, How to Get a Better Body. Will the real Doc Ock please raise his hand? In The Amazing Spider-Man number 3, which came out in July 1963, a scientist named Otto Gunther Octavius plugs a device directly into his brain to control 4 extra robotic arms. The mental limbs, which operate as smoothly as his natural appendages, allow him to work safely with radioactive materials. Each of Dr. Octavius's limbs is able to operate independently in the same way you might steer with one hand while changing the radio station with the other and depressing the gas pedal with your foot. Unfortunately for Dr. Octavius, an explosion damages his brain and dooms him to a life of villainy. Guided by a new sense of immortality, he capitalizes on his extra arms to break into safes, scale buildings, and pioneer new methods of multiple-hand combat. Under the spell of his revised personality, he becomes known as Dr. Octopus, or Doc Ock. When the comic book debuted in 1963, it was pure science fiction to imagine the brain could be attached directly to and could effortlessly control robotic limbs. But the idea has made a surprisingly rapid shift from fantasy to reality. Earlier, we witnessed the brain reorganize itself when a person lost a limb, as when Horatio Nelson's arm crossed paths with the musket ball. But that's only the input half of the story. On the output side, the cortex that drives the body, the motor map, adjusts itself as well. When the nervous system figures out that a previously existing limb is no longer available to control, the cortical territory devoted to it shrinks. The brain reorganizes to match its new body plan. Consider the case of a woman we'll call Laura, who lost her hand in a traumatic accident. Her primary motor cortex began to shift over the course of weeks. The brain areas that controlled the neighboring arm muscles, like her biceps and triceps, slowly annexed the cortical territory that formerly operated her hand. We could phrase this another way. Neurons that previously drove her hand were reassigned their job duty, now joining the team of the upper arm muscles. Laura's motor map was measured by shooting small magnetic pulses across her skull, a technique called transcranial magnetic stimulation, and noting which muscles twitched as a result. By this technique, researchers were able to watch the territory devoted to her upper arm muscles expand in a few weeks. For now, we'll concentrate on why the motor system adjusts itself like this. The answer? The motor areas optimize themselves to drive the available machinery, and this principle opens the door to many possible body plans. No standard blueprints. One doesn't need prosthetics or brain surgery to try out new bodies. The developing field of avatar robotics allows a user to control a robot at a distance, seeing what it sees and feeling what it feels. Take the shadow hand, one of the most intricate artificial hands in existence. Each fingertip is equipped with sensors, which feed their data back into haptic gloves worn by the user. Sending data over the net, one can control a robotic hand in London from Silicon Valley. Other groups are working on disaster recovery avatars, robots that are sent in after earthquakes, terrorist attacks, or fires to be piloted by drivers sitting somewhere safe. I haven't heard yet of people using strange-bodied avatars, but they certainly could. Just as the brain learns skis, trampolines, or pogo sticks, it could learn to interface with a weird and wonderful avatar body. Although avatar robotics will allow a small number of people to try out extended or strange bodies, it is frightfully expensive. Luckily, there's a better way to try out different body plans inside virtual reality. Inside a simulated space, you can make massive changes to your body plan instantly and inexpensively. Imagine looking into a mirror in your VR world. You lift your arm, and you see your virtual avatar in the mirror raise an arm. You tilt your neck, and the avatar tilts its neck. Now imagine that your avatar has not your face, but that of an Ethiopian woman, a Norwegian man, a Pakistani boy, or a Korean grandmother. For the reasons that we just saw about how the brain determines selfhood, if I can control what it does, it is me. It takes only a few minutes of prancing around in front of the mirror to convince yourself that you now inhabit a different body. You can then walk around in the virtual world as a different person, experiencing life through a modified identity. Self-identity is surprisingly flexible. Researchers have been studying in recent years how taking on the face of a different person can enhance empathy. But taking on a new face is just the beginning. In the late 1980s, because of a coding accident, the VR study of unusual bodies began. A scientist was inhabiting the avatar of a dock worker when a programmer accidentally made his arm enormous, about the size of a construction crane, by inserting too many zeros into the scaling factor. To everyone's surprise, the scientist was nonetheless able to figure out how he could operate accurately and efficiently with his mega arm. This led thinkers to wonder what kinds of bodies could be occupied. The virtual reality pioneers Jaron Lanier and Anne Lasco rendered an experience in which people inhabited the bodies of 8-legged lobsters. Your 2 arms controlled the first 2 legs of the lobster, and the programmers tried out several complicated algorithms to control the other legs. It was tough work to control the 8 legs of the lobster, but apparently some people were able to make it come to pass. Lanier coined the term homuncular flexibility, pointing to the surprising elasticity of the brain's representation of its body. Some years later, Stanford researcher Jeremy Bailenson and his colleagues set out to test homuncular flexibility more scientifically. They asked whether people could learn to accurately control a third arm in VR. When you strap on the VR goggles and grasp the 2 controllers in your hand, you can see your own arms in the virtual space, and you see an additional arm as well, offering itself from the middle of your chest. The task is simple. Touch a box as soon as it changes color. But there are lots of boxes, and to do well, you have to employ all 3 arms. The first 2 virtual arms are simply controlled by your own arms. The third arm is controlled by rotating your wrists. Within 3 minutes, users got it. They could accommodate to the new body plan as measured by task performance. There's no limit of physiques and frames to explore. Imagine finding a virtual tail protruding from your tailbone, accurately controlled via your hip movement, or becoming the size of a golf ball, or the size of a building, or having 6 fingers, or becoming a housefly with wings, or, like Doc Ock, becoming an octopus. Marrying the flexibility of the brain to the burgeoning creativity of the VR design world, we're moving into an era in which our virtual identities will no longer be limited to the bodies that we happen to have evolved. Instead, we can now speed up evolution from eons to hours. We can explore bodies that Mother Nature couldn't dream of, making virtual avatars neurally real. And an interesting possibility is that changing your body might change your mind. One study concluded that college students who use avatars of senior citizens are more likely to put money in a savings account, that men who take on a female avatar behave in a more nurturing manner, and that people who witness their avatars exercising are more likely to subsequently exercise. In the world of fiction, such a body change was proposed to underlie Doc Ock's villainy. The idea was that the rewiring required to accommodate 4 extra appendages actually changed his thinking. In other words, who we are depends on how the whole brain is wired. Tweak the body, and you may tweak the person. As a real-life example, consider the metal smelter Nigel Ackland, who lost his forearm in an industrial accident. He was a physical and emotional wreck. But then he got a beautiful bionic arm installed. His brain sends commands to his remaining nerves and muscles, and those signals get interpreted to move the hand smoothly in more than a dozen different motions. But here's the kicker. Ask Nigel to turn his wrist. He'll hold up his arm and rotate his hand, and it keeps rotating around and around on its axis. It continues to turn like a slowly spinning top as long as he wants it to. Nigel has a better body than you do, and by that I mean one with fewer constraints. When the bioengineers made this hand, they realized there's no particular benefit to sticking with the restricting ligaments and tendons that limit our movements. Presumably, Nigel can think thoughts we cannot, like keep my hand rotating or install a light bulb in one motion.